Hello, good day. It's our online lecture series. I'm Boris Jeremic, professor at UC Davis. Together with me are Han Young, Dr. Han Young at UC
Hello.
Davis, and Mr. Heshen Wang, also at UC Davis. I don't know if you see them. We had some issues with screen sharing. They are co-workers for last years or so, last 3-4 years, and they developed many of the things that you're going to learn about today. And today we're going to talk a little bit about incremental elastoplasticity, in particular the explicit constitutive solution. The last time we presented the general introduction to elastoplasticity, and if you might remember, one of the big issues was finding delta lambda, the consistency parameter. So today we're going to talk about that. You remember we defined the actual elastic plastic problem in previous lectures. We define elastic plastic model, we define elasticity, yield function, plastic flow directions, and hardening softening function. And from the finite element level, we have an increment in displacements given here. Here's an increment in displacements. And for this increment in displacements, we can find an increment in strain by essentially doing a small deformation definition of strain. This is essentially initial notation, 1/2 of partial derivative of delta ui over delta xj plus partial derivative of increment in delta uj over dxi. For that, we need to solve for consistency parameter because that is needed to find out what's the plastic strain. This delta lambda multiplies mij, the plastic flow directions. And we need to find what are the increments in internal variables because that's also multiplying the delta lambda, the consistency parameter multiplies the hardening softening function. You might remember everything is incremental. We define input, we subdivide our loads into loading stages. Each loading stage, and loading stages might be as simple as a simple self-weight or construction process, excavation, some service loads, some hazard loads, and so on. Each of these loading stages is subdivided into increments, and each of those increments is further subdivided into iterations because we would like to iterate toward equilibrium. Once we go through all these loops, we finally end up with the output. Through all the loading stages, each loading stage, all the increments for loading stage, and each increment has to go through a number of iterations to satisfy equilibrium the way we define. Today's lecture is about explicit, so-called forward Euler. So we don't really have to iterate over the equilibrium because we assume that our steps are small enough and that there's no need to iterate over the equilibrium. Although again, it's a very good idea to do that. Incremental elastoplasticity components of every single elastic plastic model. There are 4 main components. The elasticity, you have to define elasticity. You have to define the yield function, a function of the state of stress and internal variables. You have to define plastic flow directions. Once the material yields, what are the actual directions, mij, in order to be able to define the plastic strain, increments in plastic strain. And finally, you have to define hardening, softening rules so that you can find the actual change in internal variables, the hardening or softening of the material. Incremental plasticity, we make an assumption of small strains, small deformations. We talked about it last time. We can therefore do so-called additive decomposition of the strain into elastic and plastic parts. We know that elastic relationships hold, at least when the material is elastic. And we have this plastic flow rule and hardening, softening that can be isotropic, anisotropic, or distortional hardening. We talked about this as well, so-called Karush-Kuhn-Tucker conditions. They have to be satisfied simultaneously. Yield function has to be always less than 0 or equal 0. Plastic consistency parameter has to be greater than 0 or equal to 0. And loading unloading function, F times delta lambda condition, has to be equal to 0. So these 3 have to be satisfied at the same time. What does that mean? If you have elastic behavior, then F is less than 0. Therefore, your delta lambda has to be equal to 0. If delta lambda is equal to 0, going one slide back, that means that there's no plastic strain and there's no hardening softening. Going forward, on the other hand, when when material is elastic plastic, yield function is equal to 0. Therefore, delta lambda has to be greater than 0. And let's just stop at these two conditions. If F is equal to 0, delta lambda has to be greater than 0. Going one slide back, that means that you do have plastic strains and you do have some hardening, softening that is happening to the material. Going forward, again, if material is elastic plastic, yield function equals to 0, delta lambda is greater than 0. What follows from this too is that if material is elastic plastic, any increment in yield function is not allowed, has to be equal to 0. And this is the condition that's used to derive the actual elastic plastic explicit solution. Therefore, F either less than 0 or F equal to 0. F greater than 0 is not allowed, according to this theory. And also there's one more condition whereby delta lambda can be equal to 0 and F can be equal to 0. This is happening very rarely. It's a so-called neutral loading, and it's really not of any practical interest because, again, this condition happens very, very rarely, and so we will not spend much time on that. Graphically, here's the yield function. This line here, this is a space, this is a line, this is a function, a surface essentially in stress space. In this case, we represent stress by 3 main components. So we're able to see this in 3D. Let's say that we have a state of stress that's inside yield surface. If you're inside yield surface, your state of stress is less than 0. Therefore, you have elastic behavior. Let's assume that you apply an increment in strain that comes from an increment in displacements. And that increment of strain is going to drive your material state of stress up to this point here. For explicit algorithm, what needs to happen is one needs to find a point where the actual stress path crosses the yield surface. So this point is important, so-called cross point. Once you find that, then you say, well, I have actually 2 steps here. I have one step that goes from my current state of stress to my stress point, the cross point. And then I actually have an elastic plastic step that goes from this cross point up to my predictor point. You note that this predictor point is outside the field surface. Therefore, that's a state we do not allow. This is where F is greater than 0. We do not allow that. So we go back a few steps and we use this condition here that says that dF is always equal to 0. We go through a little differential geometry and we are able to find this point right here. This is the explicit forward order solution of the state of stress. You note that this state of stress is outside the field surface. It is on a tangent plane that goes through this cross point, and that is fine. This is our differentially small assumption that everything is differentially small. So we do end up with a tiny error that drives our stress out of yield surface, and that's what happens all the time with explicit solution. There's a full derivation of how these are obtained in lecture notes in section 104.3. Our solution really is based on so-called elastic predictor plastic corrector approach, where we have this next solution. This is the sigma n+1 would be equal to predictor solution minus the so-called corrector solution. This corrector solution, and then we essentially derive this solution here that increment in elastic plastic stress is equal to an increment in strain here. So here's an increment in strain, and here's that same increment in strain, just different indices. Those are dummy indices, so that makes no difference. So increment in strain times elastic stiffness, and then increment in strain times the plastic stiffness. And that is going to give us this solution right here, the elastic plastic solution, the sigma n+1. And our increment will be actually from this point here, to this new point right here. Change, if you have hardening or softening, there will be also change in internal variables, and that change is given through this equation. So as I mentioned, for this increment in strain, you have elastic stiffness and plastic stiffness. When you subtract plastic stiffness from elastic stiffness, you end up with the so-called tangent stiffness. That's the one that's used on the finite element level, and that's an important stiffness because that's the one that we use to derive elastic plastic stiffness of the whole finite element method. This particular one is made up of the elastic component right here and the plastic component right here. This plastic component is made up of elastic stiffness, plastic flow directions. This N is a normal to the yield function. Again, elastic stiffness. Again, N and N, that N is the normal to the yield surface, dF over d sigma. M is the plastic flow direction. And these two are this is the hardening function, and this is the derivative of yield function with respect to hardening internal variables. Again, full derivation is given in lecture notes on page 104.3. So with that, we'll just make a few comments about the explicit algorithm. It's relatively simple. You only require first derivatives. If you go back and look here, this M is the flow direction that's defined by the definition of a model. N is the first derivative of yield function with respect to stress. And then this is the first derivative of yield function with respect to internal variables. And H, again, is a function defined by the model. So that simplifies life a lot, first derivatives only. Again, in lecture notes, that section 104.3 and sections after that have full derivatives for a number of different material models. It's a fairly fast algorithm. It's a single-step algorithm. There are no iterations. However, you do end up with error. It's somewhat inaccurate. If you have sometimes larger steps, you will accumulate this error. You also need to find a cross point. This point here needs to be found for each step that comes from inside and ends up outside. This is a very popular algorithm, explicit, and it's used in most, if not all, commercial codes. Very few codes do use implicit, the one we're going to talk about next, but for very simplified models, for von Mises, and because in that case, the actual integration comes up to so-called radial return, so it's a very simple algorithm. Again, this explicit algorithm, the so-called forward Euler algorithm, is very popular because it's very simple, very fast. It does introduce error, but people like it nevertheless. This algorithm works well with global explicit algorithm. It does not guarantee equilibrium, far from that. It actually ends up out of equilibrium on the local level and on the global level. And the claim is that your steps, if your steps are small enough, you will not be that far from equilibrium. That claim is not true all the time. It has to be proven. It has to be demonstrated that's true. So with that, we'll stop this. Again, this is all these developments are parts of Real Easy Simulator. You can find many examples, and so now it's up to users to work out, to actually play with those examples and learn more about how to do this explicit modeling, and you know, for different step sizes, you can see how the error increases and so on. Next, we're going to talk about implicit backward Euler solution. So with that, thank you very much, and I'll see you during the next lecture. So let's see.